Welcome to presentation. Thank you so much for giving me the wonderful opportunity to say something on my selected topics. Effective fault tolerance in cloud computing using hybrid technique. And especially thanks our honorable chief guest and teachers who are listening. I'm presented by Mustafizur Rahman, MSc Engineering, Duet Gazipur, and supervised Professor Dr. Mohammad Abdullah. This presentation outline: introduction, background study and problem statement, motivation, objectives and contribution, proposed algorithm for effective fault tolerance, example of a binary operation if error are occurred, experimental setup and result analysis, comparison proposed effective fault tolerance with existing techniques, conclusion and future work. Introduction. Cloud computing is a model for enabling ubiquitous, convenient, on-demand access to a shared pool of configurable computing resources. For example, network, server, storage, application, and services. Various features are included in cloud computing, such as on-demand access, scalability, cost reduction, minimum management effort, device location independence. Critical applications require reliable cloud environment, such as scientific research, financial, safety critical applications. Transient faults may affect such as network connectivity, availability of services, and response errors. The single bit, multiple bits, and bus bits errors are occurred for transient error in cloud environment, such as operand types error, operation error, operation types error. Different types of communication error, such as packet corruption, packet loss, timer error. Introduction to effective fault tolerance. Fault tolerance is an effective step that enables a system to continue operating even in fault environments. To ensure fault tolerance in cloud, there are two types of available techniques: reactive fault tolerance and proactive fault tolerance. Reactive fault tolerance policies detect the fault after it is occurred, such as checkpointing, replication, retry, and task resubmission. And proactive fault tolerance prevents the fault by predicting beforehand, such as software rejuvenation, load balancer, preemptive migration, and self-healing, etc. Background study and problem statement. M-Aziz ETL proposed a hybrid fault tolerance model to ensure availability and reliability of cloud applications. It detects and corrects errors after the errors are occurred. The reliability depends to finish tasks within deadline. E. Abdullah Fatih ETL proposed a reactive fault tolerance technique that failed tasks are re-executed by the highest reliability of available virtual machine. The limitations are given below: wastage of more resource, rescheduling the failed tasks to available virtual machine. M. Amon ETL proposed a reliable platform in cloud application using an algorithm for selecting the most suitable fault tolerance technique. N.J. Amir ETL proposed a hybrid fault tolerance protocol to handle both crash and malicious failure in a public or private cloud environment. M.K. Bokuro ETL implements an algorithm periodically monitors the progress of jobs on virtual machine and report the stalled job due to failed virtual machine to fault tolerance manager. Arifin ETL proposed a parallel computation hardware architecture instead of existing serial CRC in the high-speed communication. Motivation: the CRC is unable to detect the bus length error. Maximum degree of device are greater than R. The probability of undetectable error of CRC is 1 minus 2 divided inverse R. CHECKSUM technique detects single bit, multiple bits error. The CRC as CHECKSUM detects CRC uses complex shift register and CHECKSUM uses binary adder circuit and detects error after multiple steps and are reactive fault tolerance. Objectives: detection and correction of the following of error in cloud computing: a single bit error, multiple bit error, any length of bus bits error, timeouts error, operations error, operands error, operand types error. Contribution: to implement the effective fault tolerance protocol to extend the data center broker policy in cloud environment using XML operation. To develop an algorithm detects and corrects the single bit, multiple bits, and any length of bus bits error after only 2 steps. And firstly, server receives the data and wants complement of it, and secondly, execute the external operation between them. The main components of cloud architecture. The cloudlet is an application which consists of million instructions. The data center broker acts as a coordinator between the cloud server and cloud provider. The cloud components are registered and store the information in a table of a cloud information service. A data center is a collection of virtualized hosts, virtual machines, processing elements, virtual networks, and virtual storage. A host consists of multiple virtual machines. The virtual machines are allocated in a host with the best fit mechanism. The processing elements execute the cloudlets. This is the proposed architecture of effective fault tolerance. And cloud consists of multiple users, and every user submits the multiple cloudlets to the data center broker. We have extended data center broker to implement the effective fault tolerance technique to detect any cloudlet or results. Data center broker knows the available resource from the CI table. The specific cloudlet are submitted to a specific virtual machine of a host in data center. The specific virtual machine is selected by the virtual machine allocation policy. After completing the result submitted to the data center broker detects any error on results. Accept the result if the outcome of error detection mechanism has no error, then accept the result to client. This is the proposed process for effective fault tolerance technique. Client takes the input data, value its one's complement, operation, and operation types. So data its one's complement are packaged and sent through the channel. And secondly, server receives the packets and unpackage all of them and waiting for all packets. When receive all packets, then external operation detect any errors on data. If error found, then resend data again from client. There are three operations: binary, vector, or matrix operation. After completing the operation, the result its one's complement are packetized and sent through the channel. Then client receives the packets and unpacketize the packets, and result its one's complement detects any error using error detection mechanism. Accept the result if the outcome of X not ET. Otherwise, request for a recent result. This is the proposed protocol for effective fault tolerance technique. The major four components here: the client, data center broker, effective fault tolerance manager, and processing. The client takes the input data operands, data types, and data its one's complement are converted. Then all data are packetized, and all packets are submitted in a frame. This frame and sent to the server. Data center broker accept the all frames and unpacketize and synchronize to data center. An effective fault tolerance manager error detection mechanism helps to detect any error on data. If error found, that resend data from clients. The zero operation, binary, vector, or matrix operation. After completing the operation, the result and its ones complete are converted, and all data are packetized, and multiple packets are submitted in frame. These frames are submitted to data center broker, and data center broker takes effective fault tolerance manager helps to check the any error on result its one's complement. If client accepts the result, the XNOR outcome is 0. Otherwise, resending the execution operation again. This is the proposed sequence diagram of iterative fault tolerance technique. There are n numbers of data ones complement and operation types and operands, all data packetized and sent to the data center broker, and sent the data center broker and fault tolerance manager detects any error. And this always detects any errors from here. If find any errors, then resend data from the client. There are three operations: binary, vector, or matrix operation. After completing the result, it's one's complement, and its error detection manager helps to detect any error and result it's one's complement. The error detection mechanism detects any error and try to find any errors on data and its one's complement. If find any errors, then re-execute result and resend data again to the broker. Broker sent the result to the client. Client accept the result. This is the example of a binary operation if error is occurred. This is the value 112 and value 28. And value 1 it's one's complement and value 2 it's one's complement. The server accept the value 1 and value 2. Then XNOR operation value 1 and it's one's complement. We can observe here. Value B3 position of one's complement has since 0 to 1. And similarly, in here, value 2 B2 position has changed 0 to 1. So the XNOR operation is not 0. So request resend data again from client. In the server section, the result is one's complement and the summation or 20 and B3 client accept then after completing the result, client accept the result, receive the result, and it's one's complement. Then observe here B3 position 0 to change 1. That means XNOR operation is not 0. So request to server, re-execute the result and send to the client again. This is the experimental setup of client machine and server machine. The processor of client machine is Intel Core i5 and server machine is Core i7. The processing core of client machine is 4 and server machine is 4. The processing capacity of client machine is 1000 million instruction per second and server machine is 3000 million instruction per second. The memory of client machine is 4 GB and server machine is 4 GB. The storage of client machine is 1 TB and the server machine is 1 TB. The bandwidth of client machine and server machine are 1000 GB. The integrated development tools of client machine and server machine are Visual Studio 17. The application of client machine and server machine are C#.4.5. This is the time comparison of CHECKSUM, CRC, and effective techniques. We can observe the performance from the bar graph. We have illustrated here x-axis shows the target length, minimum instruction, and y-axis shows the execution time according to base size of data. When base size 10 kilo data, CRC, our system reduces 1.26 seconds, and 4 kilo data, our proposed EFT's technique reduce it 29.95. So always we have observed here, our proposed system is more better performance than CRC and CHECKSUM. This is the coverage of different types of error coverage. Data flow errors here. Total injected faults are 200, and total activation fault of CHECKSUM is 103, and CRC is 135, and proposed AFT 138. The operand types error of CHECKSUM is activated 9, and CRC is 5, and proposed EFT is 7. The operand error of CHECKSUM is 69, and CRC is 86, and EFT is 70. The operation error of CHECKSUM is 21, and CRC is 33, and proposed EFT 42. And operation types of CHECKSUM 3, and CRC 5, and EFT 7. The silent data corruption of CHECKSUM is 0, and CRC is 3, and proposed EFT is 1. The other error CHECKSUM is 1, and CRC 3, and proposed EFT 11. The coverage of CHECKSUM is 96.18, and CRC is 97.78%, and proposed EFT is 99.98%. The summation of all operand types, operand error, operation error, operand types error, silent data corruption, other errors, summation of false equal to false activation detected equal. That means all are summation equal to 103, and all are summation activated false are equal to 135 activated false detected. And our proposed system, all our summation parameters false activated, then our effective fault tolerance detects the error 138 are equal. We have observed here our proposed system is more better performance than others, CHECKSUM and CRC. The comparison of effective fault tolerance with existing technique. The parameters of this the bits error of CHECKSUM is single bit, multiple bits. CRC is single bit, multiple bits, and bus bit error. I propose EFT is single bit, multiple bits, and any length of bits error. The operation of CHECKSUM is binary adder, and CRC is binary division, and propose EFT is XNOR operation. Order of CHECKSUM is parallel adder, and CRC is shift register, and EFT XNOR bit. The technique of CHECKSUM. The CHECKSUM technique is reactive fault tolerance, and CRC reactive fault tolerance, and propose EFT is corrective fault tolerance to detect any errors. Undetectable error of CHECKSUM is less, and CRC is probability of undetectable 1 minus 2 minus R. The coverage of EFT is 99.98% coverage, so undetectable error is 0.02%. The burst net of error detection of CHECKSUM is unable, and CRC unable to detect maximum degree of device are greater than R equal to 1664. And EFT able to detect any length of burst errors. The detection of error detection of CHECKSUM is more than 2 steps. The CRC have multiple steps to detect after multiple steps. The proposed EFT error detects after only 2 steps. The conclusion and future one. The proposed EFT has the high reliability. It detects and corrects single bit, multiple bits, and any length of burst bits errors. The coverage of proposed EFT scheme is 99.98%. The coverage of CRC is 97.78%, and the coverage of CHECKSUM is 96.18%. The EFT has the highest coverage. The proposed EFT is 1.70 times faster than CHECKSUM technique and 3.06 times faster than CRC technique. In future, we can apply the different level fault tolerance scheme which can detect more errors and correct them without resetting or re-execution. This is the reference paper here. The most important paper are added here. I have selected only 11 papers among the 19 papers. Thank you, everybody. Thank you. Assalamu alaikum.